We live on a restless planet. From the gentle whisper of a breeze to the terrifying roar of a hurricane, our world is a symphony of sound, a constant testament to the dynamic forces that shape our atmosphere. For millennia, humanity has been captivated by one of nature's most dramatic auditory displays, the crack and rumble of thunder, the echo of lightning's fury. It is a sound that evokes primordial awe, reminding us of the immense power held within our skies. But what of other worlds? What symphony plays in the thin, alien air of distant planets? Could a similar, electrifying ballet unfold on a world like Mars, a place often imagined as silent and still? This question, once confined to the realm of science fiction and theoretical physics, is now being answered, not by a poetic musing, but by a tiny microphone, hundreds of millions of kilometers away. For centuries, astronomers turned their gaze skyward, charting the movements of celestial bodies, discerning patterns, and slowly unraveling the mechanical dance of the cosmos. Galileo, with his humble telescope, revealed moons orbiting Jupiter, challenging the geocentric worldview. Later, powerful instruments unveiled the intricate tapestry of galaxies, nebulae, and the echoes of the Big Bang itself. But until very recently, our understanding of other planets was largely visual, a tapestry woven from light and radio waves. We could see the swirling dust storms of Mars, the immense Vias Marineris, the polar ice caps that waxed and waned with the seasons. We could infer atmospheric composition, wind patterns, and geological history. Yet, one sense remained largely untapped: hearing. Imagine, for a moment, the sheer audacity of sending a microphone to another planet. When NASA's Perseverance rover touched down in Jezero crater in February 2021, it carried an array of cutting-edge instruments, designed to search for signs of ancient microbial life and collect samples for eventual return to Earth. Among these sophisticated tools, nestled within the SuperCam instrument, was a small, unassuming microphone. At the time, many wondered about its purpose. Would it merely capture the faint hiss of Martian wind, or the whirring of the rover's own mechanisms? The Martian atmosphere, after all, is incredibly thin, less than 1% the density of Earth's. Sound, as we understand it, propagates through vibrations in a medium. A thinner medium means less efficient sound transmission. So, what could we possibly hope to hear? The early recordings were indeed subtle, the quiet hum of the rover, the faint whistle of Martian gusts, giving scientists an unprecedented acoustic profile of a truly alien soundscape. These initial sounds were fascinating, offering new ways to study the Martian atmosphere's density and temperature fluctuations. But then, something truly extraordinary happened. After over 1,300 sols, Martian days, of operation, with nearly 29 hours of accumulated audio data, a distinct, powerful signal was detected. It was not the gentle whisper of wind. It was, in all likelihood, the first recorded sound of thunder on Mars. This isn't as outlandish as it might initially sound. On Earth, lightning and thunder are primarily associated with towering cumulonimbus clouds, formed by intense convection and moisture. We see majestic lightning bolts arcing across the sky, followed by the deep rumble of thunder as the rapidly heated air expands explosively. But there's another, less common, phenomenon on Earth that offers a crucial clue: volcanic lightning. During explosive volcanic eruptions, immense plumes of ash and rock are ejected into the atmosphere. The sheer friction between these particles generates static electricity, leading to powerful electrical discharges, lightning, even in the absence of traditional storm clouds. Mars, while devoid of Earth-like storm clouds, is a world of immense dust. Global dust storms can envelop the entire planet, and smaller dust devils are a common sight, swirling across the arid landscape. Scientists have long theorized that the friction between these countless dust particles, propelled by Martian winds, could generate enough static electricity to cause electrical discharges. This is known as triboelectric charging. The question wasn't if it could happen, but if it did happen, and if we could detect it. The Perseverance rover's microphone captured an electromagnetic surge, a transient phenomenon characteristic of an electrical discharge. The spectral signature of this event was remarkably similar to the acoustic waves generated by the rover's own SuperCam laser ablation system, which uses a laser to vaporize small amounts of rock and soil for analysis. Both exhibited a lobed structure, with distinct peaks indicative of shock waves propagating through the thin Martian atmosphere. Furthermore, both showed a spectral break around 6 to 7 kHz, caused by acoustic interference from reflections off the instrument itself. This confirmed the acoustic nature and external origin of the signal, it wasn't just internal rover noise. To further validate this groundbreaking discovery, scientists recreated Martian atmospheric conditions in a terrestrial laboratory. They simulated the low pressure and temperature of Mars, introduced dust, and induced electrical discharges. Using a microphone identical to the one on Perseverance, they recorded the resulting sound profile. The generated sound signature in the lab was a near-perfect match for the signal detected on Mars. This experimental replication provided compelling confirmation, the signature detected by Perseverance was indeed that of a triboelectric discharge. These discharges weren't random occurrences. Analysis revealed patterns. For example, the rover traversed through 2 significant dust devils, and during these events, 16 distinct electrical discharges were detected. When the rover passed through the front of 2 consecutive dust storms, a remarkable 35 discharges were recorded. On Sol 1296, Perseverance was enveloped by one of the most intense dust devils ever documented. Within the vortex's core, the microphone captured 10 discharges, including the most energetic one of the entire mission. All other sensors on the rover confirmed the passage of this powerful dust devil. This direct correlation between dust activity and electrical discharges strongly supports the hypothesis that these are Martian thunderclaps, born from the friction of swirling dust. The detection also showed a seasonal variation, with more discharges occurring during periods of higher dust activity, aligning with our understanding of Martian weather patterns. Now, it's important to frame this discovery within the broader context of electrical activity in planetary atmospheres. On Earth, lightning bolts can release energies ranging from 10 megajoules to 10 gigajoules. Orbital detections on Earth, though less direct, measure in the kilojoule range. The Martian discharges detected by Perseverance, by comparison, are far less energetic, typically falling between 0.1 and 150 nanojoules. This might sound minuscule, but it underscores a crucial difference: the breakdown voltage, the electrical field strength required to cause a spark, is significantly lower in the thinner Martian atmosphere compared to Earth's denser air. In essence, Mars is actually more susceptible to electrical discharges, despite its much fainter atmosphere. It simply requires less energy to create a spark. We just needed the right instrument, in the right place, to hear it. The implications of this discovery are profound and far-reaching. Firstly, these electrical discharges can drive what we call reactive electrochemistry in the Martian atmosphere. This process can produce oxidants, highly reactive molecules that affect the preservation of organic molecules on the planet's surface. This has significant ramifications for our search for past or present life on Mars. If life did exist, or still exists, these oxidants could play a role in destroying or altering the very biomarkers we are seeking. It's a reminder that the environment of Mars is an active, dynamic one, constantly shaping and reshaping its own chemistry. Secondly, the presence of electrical forces can reduce the threshold wind speed required to lift dust from the surface. In other words, these electrical fields can make it easier for dust to become airborne, potentially influencing the frequency and intensity of Martian dust storms. This feedback loop, dust causing electricity affecting dust, could be a key factor in understanding Martian atmospheric dynamics and its enigmatic weather patterns. And finally, for future human exploration of Mars, understanding the electrical environment is critical. While these discharges are far less powerful than Earth's lightning, they still represent an electrical hazard. Future missions will need to account for these phenomena, both in terms of spacecraft design and astronaut safety. Just as we factor in radiation and dust storms, we now add atmospheric electricity to the list of environmental considerations for living and working on the red planet. The detection of these Martian thunderclaps isn't just a scientific achievement, it's a profound expansion of our cosmic awareness. For the first time, we have listened to the very heartbeat of another world's atmosphere, heard the subtle crackle of its electrical energy. It is a moment that transcends mere data points, opening a new sensory window onto the universe. It reminds us that every world, no matter how barren or desolate it may seem, holds its own secrets, its own subtle symphonies, waiting for us to develop the tools and the curiosity to listen. It is a testament to humanity's unyielding drive to explore, to understand, and to connect with the cosmos on an ever deeper level. That's it for today. If you enjoyed this deep dive, hit that subscribe button. Stay curious, and keep your eyes on the skies. I'll see you in the next one.